Hello, my name is Don Metzger. This video shows how to use an Analog Devices AD9081 MxFE eval board hosted by an Analog Devices ADS9 digital board and running under Analog Devices ACE software. In this video we will take quite a bit of time to show you how to set up the ADS9 and ACE. If you're having trouble getting your setup to work, hopefully you'll find something that could help you. After getting the system running, we will go on to show the advanced characterization that you can do using QIQ Systems Quick Receiver Pro software. If your design requirements are defined in terms of EVM rather than SFDR or THD, then this will show how easy that assessment can be. Here's the setup we'll be using. The host board is an Analog Devices ADS9. The AD9081 FMCS EBZ eval board is attached using the FMC connector. The ADS9 is connected to a PC using an USB cable and an Ethernet connection. So the ADS9 has been turned on and booted up, and what I like to do first of all is to run a PuTTY terminal to the device. You can either do this with a serial connection to the microZ board on the ADS9. I like to do SSH, and so I've got this IP address is the IP address for the microZ board, port 22 SSH, and let's open that up. And I'm going to log in as root and analog. So this is a little Linux computer running on the ADS9 board, the microZ board there. And first thing I'm going to do is do an ifconfig, and because we're connected with SSH, we already know that the internet address is 192.168.0.10. Some folks have some problems with the kind of two Ethernet setup that you need to do and things like that. I've had that problem myself. So let me show you something that might help you in getting things set up. So we're going to change directories to /etc/network and ls to take a look at the files that are in there. There's a file in there called interfaces. And so I'm just going to cat to list the contents of that interfaces file. It's a small little file. You can see here's the file contents. ETH0 is the main interface that we're connected to the PC. You can see a number sign in front of this line means don't do DHCP, do a static IP address, and then here's the IP address and here's the net mask. So if the IP addressing isn't quite working out for you in your network setup, you can go in and edit this interfaces file and perhaps change a fixed IP address, maybe make it dynamic, whatever might work for you in your network setup. So I'm just going to go back to the main directory. So this is just talking to the microZ. It's up and running. So we're feeling pretty good about our setup, at least from a network connectivity standpoint. I'm going to go over and start ACE on the PC. And it usually goes off and checks to see if there are any updates, and I'm not doing an update here. Let me go in here and show you a few things that's helpful to me in getting my setup up and running. You want to hit the settings button. You want to go to Ethernet boards. You want to go to servers, and what this is saying is this is how I connect to the micro Z board. This is that fixed IP address that it has on there, port 5000, and we're going to use the device API and auto detect what platform is there, and you want to make sure this is enabled. So that's one thing that you want to do, is get this set up right, and whatever your host IP address is for that micro Z board, that's where that goes in there. And make sure that this is enabled. So that's the first thing there. Now later on we're going to use the QIQ Systems software to interact with ACE, and so that's this IPC server. So let's go in here and make sure that the IPC server settings are ready to go. Usually this is not enabled by default in ACE, so you want to make sure that the port number is 2357. You want to make sure that this is enabled, and that will also show as a check mark up here. Anyway, that's basically it. How does ACE talk to the micro Z, and then how do other things talk to ACE? And we'll close this. Now, when you turn on ACE, it's going to go out and look for whatever eval board you've got connected and so forth. And this is usually where I have problems. Under the tools, you can use the events that will tell you some things. This is telling me it has an error even though it found the board. So events can give you some hints as to what it's having problems with if it's not finding your ADS9 micro Z board and the eval. But in this case it worked, and so that's pretty good. I'm glad that it worked this time. It seems to be a little bit too finicky. But once it does find it, you double click on what it found and it brings up the board. And I'm going to wait. You can see the spinning cursor here. I'm going to wait for just a second, and here's the configuration. One very important thing to know that this is really working is that this field right up here gets populated with some big honkin' number. If that says 0x0, then it's not really finding your chip and hardware and things like that. So this is your first step, is really finding that that's the board, and the second step is that this UID field got populated. Then we go over here and we choose a basic configuration. The one that I'm going to be using today is we're running the DAX at 12 gigasamples, we're running the ADC at 4 gigasamples, and then we'll use enough interpolation on the DAX side and decimation on the ADC side that the outside data rate will be 250 megasamples of INQ. That's the mode that I tend to like to work in to do demos. So you just go down here and you hit the apply button, and it doesn't really tell you what's going on. That's one of the annoying aspects of this. You just sit and wait until this dialog over here changes its physical appearance. If you try and go do something else, Windows is going to tell you this app is locked. It's not really locked, but you can see now that we have changed the appearance of this, and it's become the quick configuration summary on here. So that's good progress. Now let's go and talk to the chip itself. So let's click on the chip. Sometimes that takes a little bit of time to respond there. And I'm going to go down here. These are all default settings for the plug-in for the 9081. One of the things I like to do is run this at 1 gigahertz for all of the transmit and receive channels. That's a little better centered in good bandwidth for the receive side in particular. So I just delete back all of these things and set this at 1 gigahertz for all of our transmit and receive channels. You can set this wherever you want. Sometimes you have to worry about if you're getting into the second Nyquist zone or something like that. Once you've got all that set up, just hit the apply button. Again, it doesn't really tell you what's going on. You kind of just have to be patient and wait for it to give you some indication that it's done what you asked it to and it's ready to move on to the next step. Okay, so this changed its physical appearance, and that's how we know that it was done with this. Next thing we do is we proceed to the analysis. Click that once. I don't tend to like to look at waveforms. I tend to like to look at the FFT stuff, so I turn off the waveform stuff. Click on this area here. I don't ask the system to do any analysis for me, so I go into the analysis and say none, and I close that, and I close the results, and down here at the bottom it just says run continuously, so let's hit that. So what we're getting now are the 4 ADC channels. They're all running, they're running at a gigahertz, and the external INQ sample rate is 250 megasamples per second, so about 200 megahertz usable bandwidth. And the number of samples that each of the channels is gathering is 64K, where the K is the digital 1024 number. Alright, so that's up and running. That looks good. Let's stop the captures at this point. Unfortunately, ACE does not allow us to talk to it while it's doing captures and ask it to go get some data. If this is running, then ACE will generate errors and not like that. So you have to stop what you're doing here when you start talking to ACE externally. Alright, so let's make something more interesting to look at than just a noise floor. I'm going to start up QIQ Systems software quick generator just to make some waveforms for us here. I'm going to do a 64 QAM signal, so start up the PSK QAM generator, choose 64 QAM. I'm going to do a 50 megasymbol per second signal and do 5 times oversampling to get us to IQ data. So that'll give us a sample rate of 250 megasamples a second. I'm going to use root race cosine alpha of 0.3. And down here, the number of samples has to be a multiple of 256 for the way in which ACE and DPG plays the waveform. That's one of their restrictions. And then it should also be a multiple of the oversampling rate so it doesn't glitch as it plays in a circular buffer there. So 128,000 samples is a good number here. So let's apply that. Let's go make it with the start button, and then let's go save it. And I'm going to save this as a TXT file, and I'm going to go in here and modify the name of this file. I'm going to call it Block IQ because DPG Downloader, the software we're going to use to play this waveform, wants it to be I and then QQQQ in the file. So block I, block Q. Most things do an interleaved I and Q, but this is just a different file format. So we generate a file name here that is tells you what's going on in it, because the .txt file has nothing to describe the waveform that's in it. So we save that, and we're done with making the waveform. And now let's call up the program DPG Downloader or DPG Lite. And the first thing that you want to see is you want to see that this has found the board there. So I'm going to go add a data file, the data file that we just made. So that's this one here, the 64 QAM in the block IQ format. Okay, and now I go and say let's use that in channel 0 or DAC 0 there. Let's do a download the selected file. So it's been downloaded to the board, and then we hit play. So the waveform is now playing on the DAC side of the MxFE, and we can go in here on ACE and run continuously, and now we can see that channel 0 is that light blue trace, and it's got a waveform in it. So you can create multiple files, play them in different channels, and so forth. Again, we're going to go back in here and we're going to stop this because we have to stop ACE in order to talk to it with other software. Alright, so at this point, if you are just interested in this video from the standpoint of help me get my board up and running, we're done at this point. We've shown you how to connect things, how to get it up and running, how to create waveforms and run some real stuff through the system. We're going to go on now though and do more advanced analysis. This software ACE will give you some analysis in there. It'll show you spurious free dynamic range and total harmonic distortion, things like that. But nowadays most of our design requirements are expressed in other ways. So I'm going to start up the QIQ Systems software called QIQ Receiver Pro. Now on this computer that we are running, I'm going to run both QIQ Receiver Pro and ACE on the same computer. At the moment, when we try to connect to ACE remotely over the network on another computer, sometimes that works, sometimes it doesn't work. So we are just doing local connections. So you need to run the QIQ Receiver Pro software on the same platform you're running the ACE software. So that's the first requirement. Another requirement is ACE does not have any mechanism for us to just get the data out of ACE. Give me a buffer full of data, like IIO will do. So ACE will write things to a file. So the first thing we have to do is we have to create some location on this computer where we can exchange data. So I'm just going to do that on my D disk. I just create a folder called ACE data, and I'm going to tell ACE, capture some data, write it to a file, then our software will go in there and read that file, and that's how we get the data out of ACE and make the system work. If this folder subdirectory does not exist, then ACE won't write to it. So this must exist somewhere on your PC. Just remember where it is, create some location that you can use for this data exchange. And if you go in there and look, there'll be all sorts of stuff that ends up being dumped into this folder over time as you run the software. Okay, so that's an important aspect of this, is you need to create some directory so that we can exchange data. One of the things when you bring up QIQ Receiver Pro, usually you want to set what are the active windows. So I like input waveforms, input spectrum. This is the data that is being gathered from the system. I also like input spectrogram. So input implies this is the raw data that we're getting from the ACE captures. I will also put in processing spectrum at times, and then the constellation is the final symbol constellation, and then measured results. So those are the typical ones that I run, and it ends up occupying a window about this big. So you might, if you're starting up the software, expand the window about this size, pull up those different windows. We are doing an ACE connection, so under Instrument, go down here to ACE connection. And this is where we tell it two things. What are we talking to? We're going to be doing AD9081 captures here. We have other boards that we support under ACE. And then this is that directory that we created. I guess actually we had this as the D disk. The D disk ACE data. Alright, so now we've told the system what kind of board we're working with and where we want that data to be exchanged. And then we want to bring up, basically all we can say is which receiver channel or you want, which ADC number are you wanting to get data from. And you can do it from any of the four, and the way I've got the board hooked up with just a loopback cable from DAC 0 to ADC 0, I want to gather the data from ADC 0. Alright, and then finally I'm just going to start this in SpecAn mode. So let's click this as Spectrum Analyzer mode, and then you want to make sure that this button is clicked because we're going to gather data from the ACE instrument. Alright, and then we just hit start. You don't start the captures on ACE, just leave ACE alone. And immediately this is going to tell you down here what's going on. Alright, so all we're doing is kind of a spectrum analyzer mode where we're not doing any post-processing or anything like that. So this is the I and Q data that we're getting from ACE through that file transfer mechanism. This is the spectrum of that IQ data. This is a spectrogram. So joint time frequency. Frequency is horizontal, time is vertical. I like this plot because if our circular buffer has a glitch in the waveform, you'll see some spectral splatter here, horizontal lines in that. And so we don't see any of that. So we're doing good in that regard. And then we've got a few measured results showing up over here, but not much because we're not doing any demodulation. So I'm going to stop this capture right now. I'm going to go up to processing and say PSK QAM, and we're going to do 64 QAM, 50 megasamples per second, root raised cosine, alpha of 0.3. There we go. And start again. You'll notice after we close that dialog box that the PSK button got illuminated here. Alright, so now we have a demod happening, and you'll notice the final symbol constellation is over here, and now we've got lots of interesting things to look at in the results. So it's going to tell us we're doing 64 QAM, 50 megasymbols per second, carrier frequency is gigahertz, occupied bandwidth is 50 megahertz, that's being measured on these spectra down here. Peak to average really isn't that interesting for these, but if you're interested, that's the peak to average. Carrier to noise ratio, C over N, is an interesting thing that I like to look at. That is if the level of the power where the signal is and the noise floor. What's the ratio of this to this in an equal bandwidth and other requirements there. But carrier to noise is like 62 dB. So for a 50 megahertz occupied bandwidth, that's a pretty good carrier to noise ratio in the system. Then we go through a whole demod and we get these final symbols and we do EVM measurements and things like that. So here we go. Here's EVM, and EVM expressed as percent, or some people like EVM as a negative dB type of number, so that's in there. And then we also do some IQ offset measurements and IQ imbalance. This is a little bit more required for zero IF systems than for these direct sampling systems. You can see there's a little bit of quadrature error, fraction of a degree here that we're measuring in the system. So what I see here when I look at this is carrier to noise is this expectation of what am I expecting to see signal to noise ratio wise when I get my final data here. And this number here is a lot bigger than this number here. This number is on the order of 62 dB, but my EVM is only like minus 40 dB. So I'm a little bit disappointed in the quality of the final demod here. It's not quite as good as what I would like it to be. And the reason that that is the case is because the chip is not the only thing that's in the system here. We have a transmit balun and we have a receive balun, we have SMA connectors, we have traces on the board. There's a lot of other stuff in the system. And what we found is that if we go in here and we turn on some adaptive equalization, this is going to flatten out the baluns. The baluns have enough ripple to their response over a 50 megahertz bandwidth that they adjust what we see here at the very end. So I'm going to turn on some adaptive equalization. I think I'm also going to turn on some zero IF corrections to get rid of the quadrature error that we're seeing in here. Let's just see how good of an EVM we can get. So you just hit apply here, and now you can see how tight that constellation has become there. So I'm just going to stop things to just make the numbers a little easier to read. If you remember, this number was like minus 40 dB, which would be an EVM of about 1% in that ballpark. And now we have jumped to minus 58 dB, so much better EVM in the system here. Carrier to noise is still around that 63 dB level. And the final demod gives us close to about 60 dB down EVM numbers. So that's a pretty good result. If you need in your system these sorts of really good EVMs, then maybe in your system you need to think about putting some adaptive equalization to deal with some of the RF imperfections of just putting things on a board and using baluns and other things like that. If you visit us at QIQsystems.com, you can learn more about the software and about the different waveform types that we support, like DVB-S and 4G and 5G cell phone types of signals. And you can send us an email at sales@QIQsystems.com. Thanks for your time.